Swayam Prabha. Digital India. Educated India.
So, eventually we are going to talk about graph streaming lower bounds, okay. So, Venkatesh in his last class would have told you in a streaming model, how do you check connectivity by maintaining a spanning forest of sort, right. He may also have hinted on some other problems like, I do not know, matching he probably would have done on how to do a maximal matching on a streaming model, which ends up being a true approximation to the maximum matching and so on, okay. So, those are the, the optimistic side of things, the positive side of thing. You have a problem, you learn how to solve it, okay. Now, that's the optimistic side of things, okay. Now, there is always a corresponding, pessimistic side to it. It is like saying, okay, you have an algorithm which has this performance, and as researchers, as engineers, we keep asking, is there a better algorithm, okay. And the pessimistic side comes in to kind of put a natural limit to it. You put a limit to how best things can be. So, these are usually what are known as lower bounds. So, for example, it is known that the algorithm that we just spoke about to find the check connectivity of a graph using maintaining a spanning forest, which essentially is just the Kruskals algorithm running on a stream. If you know Kruskals algorithms from data structures, it's essentially the Kruskals algorithm running on a stream. There is a result, I won't be able to prove that, I'll prove a weaker version of that, which shows that in fact that's the best you can do. No matter how hard you try, there is no algorithm which can do the same job with less than n log n space, okay. So, these are what are known as lower bounds, okay. So, these are more not so much about algorithms, but these are more about the limits of algorithms, okay. So, you should realign your thought in that direction. So, there is, some of you I am sure, half of you would have heard these kind of arguments earlier, to show that any sorting algorithm, any comparison based sorting algorithm requires n log n comparisons in the worst case. How many of you have heard about that? Right? So, this is going to be in that kind of a line, okay. And what makes it challenging is that you are not arguing against a particular algorithm, you are arguing against all possible algorithms, even algorithms that haven't been invented, okay. So, that's what makes this lower bounds interesting, okay. But before we start speaking about lower bounds, before we get there, we will start with a game, okay. This is this comes under the area called communication games and so on. We will have these two characters whom you see in a faint watermark here, Alice and Bob. You would have heard these names before, right? Yeah, they are just placeholders for A and B, but there is actually a history to, it's like a cartoon character, we remember who invented Superman, right, who invented Spider-Man and so on. Similarly, this Alice and Bob actually has such a history. They were first used by Ron Rivest in the RSA paper, Shamir, Adliman and Rivest in their RSA paper. RSA is a very famous crypto system. So, in order to describe this cryptographic protocol, earlier papers just used to call it A and B, but they were a bit more creative people. They wanted to give characters to it. That's the origin of Alice and Bob. And then these characters kind of, like Marvel Comics has done, these characters kind of took over the theoretical computer science scene. So, not only in cryptography, in many such games, you kind of use them as characters, okay. So, in this game, Alice and Bob, imagine that they are separated far across the globe, okay. And the universe that we are talking very boringly is the set of numbers, okay. Let's say numbers from 1 to a million, okay. It could be any set, okay, but to keep my typing simpler, I just chose the set to be numbers 1 to a million. What does Alice have in her hand? She has her collection of favorite things. Okay, things in this context happen to be numbers. So, we have her collection of favorite numbers. So, A the set that Alice has is guaranteed to be a subset of universe. By the way, this universe U is known to both Alice and Bob. Okay, there is no secret there. What is not known to Bob is what is A. Okay, A, what is the set A? Only Alice knows. Maybe it's a set of prime numbers within this range, within 1 to 1 million. Maybe it's a set of even numbers. Maybe it's a set of perfect numbers. We do not know. It could be any subset of 1 to U. Bob, who is on the other side of the globe, has just one element, He's like a very picky, very choosy guy. Okay, he just likes one number. Okay, maybe he likes 1729. Okay, just one number he likes. Okay, that's what it is with him. And Bob would like to know if his favorite number is one of Alice's favorite too. Okay, mathematically, Bob wants to know if I is an element of A. Bob already knows I is an element of U. Bob already knows A is a subset of U. Bob knows U. Only thing that is left for Bob to know is whether I is also in Alice's set. Clear? Okay. Feel free to stop me at any time and ask if it's not clear. Okay. Now, this looks easy, right? But then, what makes it hard is the constraints that they are living in. Okay, they are on opposite sides of the globe. They only have a one-way channel. Okay, there's a very watered-down version of a general problem. In this setting, there is a one-way channel. Alice can send information to Bob through a binary channel. Okay, which means Alice can send ones or zeros across some very expensive channel to Bob. And the company which is running the communication link is expensive. They will charge 1 rupee for every bit that is sent. So the natural question here is, how small a number of bits, how few bits can Alice send so that Bob, knows the answer to the meaning of life. What is his biggest worry? He wants to know if I is in A. Okay, how many bits can we achieve this communication in? Okay, there is no communication possible in the opposite direction. Okay, so this slide somehow, in my opinion, summarizes the game. So please go through each point in the slide and make sure that you are on the same page. Okay, we are going to talk about 2 games. This is the first one, and these 2 games we will have to keep in our mind for the remaining part of the talk. So even those who kind of came late, I hope you will get time to go through the slide and make sure that you understand the game perfectly well. Everybody with me? You understand the game? Okay. Now your turn. What can Alice do? Can you forget about minimizing cost and so on for now? Give me some strategy for Alice to send information to Bob so that Bob would know whether I is in A. Huh. We mark it as 1. If she has it, we mark it as 0. So for all the 1 million. So how many bits will you finally send? 1 million. 1 million. Very good. Okay. I'll come to that answer, but let me just do a slightly worse answer in the beginning. Your answer is better. Okay. One thing is that Alice can choose binary encoding for numbers and then send, let us say Alice had all the prime numbers. Then she will send the binary for 2, the binary for 3, binary for 5, binary for 7, etc. Okay, and you will send a binary representation for each of the numbers in your set. What would be the total number of bits you end up sending? It will be the number of bits you need to represent one number. Are you with me? Times the size of A. Right? Because each member in A you will need to send. So this will be roughly log n. If this 1 million is what I will sometimes refer to as n. Okay, the number of elements in the set is n. The binary representation will require log n. You have seen that couple of times already. So you will need something like log n times the size of A. But if the size of A is also very large, then this could be a n log n kind of thing. If A has, let us say, half of all the elements in the universe, it could be half of n log n, which is worse than the answer I got from the audience. Okay, the answer I got from the audience is even more interesting. You just think of this universe as positions in a bit vector. Okay, so you have 1 million numbers in the universe. So you are talking about a bit vector whose length is 1 million. And each position is either 1 or 0 based on whether A contains that number or not. So if A is the set of prime numbers, the positions 2, 3, 5, 7, 11, 13, etc. in this bit vector will be a 1, whereas positions like 1, 4, 6, 8, etc. will be a 0. What is this vector called? There is a name by which this vector is known. This is called the characteristic vector of this set. Okay? It's just a name. I mean, if you haven't heard before, just keep that in your mind. This is a standard trick. It is called the characteristic vector of a set. You need to know the universe to be able to do this. Okay? Because the positions essentially are some ordering of the universe. So you really need to know the universe. You have to agree upon an ordering of the universe to be able to represent a set as a characteristic vector. So in one line, what Alice can do is to send the characteristic vector of A to Bob. Since the characteristic vector has 1 million bits, the cost that Alice will have to pay is 1 million rupees to the channel company. What would Bob do? Bob's index may be 1729. It scans through this bit stream that it got from Alice, looks position 1729. If it is 1, he is happy. If it is 0, he is rejected. Okay, I mean his favorite number is not Alice's favorite number. So is this idea clear? Okay. So this kind of already proves that the minimum number of bits that you need to in this game, the minimum number of bits that Alice have to send is already n. Okay, we have proved an upper bound. Okay, this lecture is about lower bounds, but I want to make sure that you understand any algorithm kind of gives you an upper bound. Is that clear? Right? Because there is one protocol, there is one strategy which I got from the audience which suggested how to send this or how for Bob to understand the answer to his question by paying n bits. Okay, so if there is a worse algorithm like the cardinality of a log n that I said, that's not going to bother us because we have something which is n, which is better than n log n, so we will go for n. But now the question is, I mean, are we the smartest people in the world? Right? We may not be. Is there even better algorithm which can do better than n? That is how a lower bound kind of thinking comes in. Okay, so that's your second task now. Can you think of showing that you really cannot do better than this? You need to send n bits for this game to work in the worst case. Okay. More than the answer, it's important that you start thinking. Finally, when you hear the answer, it's going to be like almost obvious. Okay, it's about how you argue. What is your gut feeling?
Alice can send the numbers, the list of numbers which she has, and then Bob maybe can do research on it.
Okay, so good attempt. In fact, this was the first attempt that I mentioned about. Bob, how he is going to find it, we don't bother. Time is not a resource here. In the sense, time is free. Okay, so it is more about how many bits you have to transmit. But in the answer that you suggested, in order to represent one number from an universe of 1 to n, you will need log n bits. So the amount of communication you are going to do is size of A times log n, which for large A's can be bad. Okay. So it might be more closer to n log n than n. Since n is smaller, we are using that. Okay. So back to our lower bound question. Do you think we can improve this? Somehow the way I have posed the question have left out the, kind of I have already given out the answer that it is impossible, but then any idea? Okay, I mean here don't worry if you don't get an idea, because the idea is something, in this case it's more about how you argue. Okay, so let me ask a sub question. Okay, I make the following claim. I want to state that however Alice's choose to communicate, whatever compression, encoding, whatever scheme she does, finally when the information reaches Bob, okay, this is the key part, Bob should have enough information to decipher the entire set that Alice has. Even though Bob is interested only in checking whether I is in A, I claim that the amount of information that reaches Bob should be sufficient to completely determine what is A, not just whether I element of A. Okay. Alice really cannot hide anything. Alice has to be completely open in this for this algorithm to work. And there is a simple reason for that. What is the simple reason for that? Yeah, first of all, that's the starting point. The communication is one way. By the way, if it was the, okay, I'll ask that question later. The communication is one way. So Bob has no way to give any hint to Alice. Okay. You think about this, exam copying scenario. The person sitting in the front can give some information to the guy in the back, but there is no way you can do the opposite. Okay. Yeah, but now can you build on that argument? That's a starting point. So
this is the maximum number Alice can send, or sorry, Bob can receive, or minimum, because he needs to know each and every bit.
But
Either 1 or 0.
why? Now you have given me the first step and the third step, but I feel like a second step is missing.
Because he has only one number to verify. But where it is,
Perfect. Yeah, that's the key argument. Okay. Even though Bob only is worried about whether I is there in the list or not, Alice doesn't know what is this I. Okay. So it is as if, if Bob's number was 1, Bob should be able to make out. So Alice should make sure that the status of whether 1 is there or not in Alice's set is known to Bob. Same thing with 2, 3. Okay. The problem here is that Alice doesn't know I. So whatever she sends, it's a one-shot communication, right? Whatever she sends, Bob should be able to verify. Whatever be his I, he should be able to verify, which means Bob should somehow be able to decipher what entire A is. Okay. So this has to be a completely lossless protocol. You cannot hide any information. Bob should get whatever message is being passed. That message should be a very trustful, zero error, complete information encoding of A. Okay. Are you with me? This is a key point. Now, for that, how many bits do we need? Okay. It's not necessary that you have to send the characteristic vector. Maybe you can put the characteristic vector through a zip algorithm. You have all the gzip or whatever compression algorithm on your computer. Compress it and send, right? Why not? So we need one more argument to say that maybe there are many schemes, but on the worst case, you will still end up requiring n bits. Okay. This is again just a cardinality argument. How many different possibilities does Alice have? Which is equivalent to asking how many sets A are possible in this game? 2 power n, exactly. So you are clear, right? If you have a universe of n, you have 2 power n subsets of that. Now Bob should be able to distinguish all these 2 power n cases. The number of cases is not n, the number of cases is 2 power n. And in order to be able to distinguish 2 power n things, you need at least log of 2 power n, binary log of 2 power n, which is n bits. That finishes the argument. Are you all with me? Okay. So make sure that you understand. This is the summary of what we have been saying so far. Make sure that you are on the same page. The bottom dark thing, the lower bound is what we are going to critically use later on. Any questions? Okay. Are we ready for the next game? Was there a question?
So if Alice is sending the exact set that he has got, why do we need like another thing to check if it is any of the 2 power n subsets? Alice is sending what all she has got. That's our characteristic.
Good. I understand your confusion. Okay. That is because you are still thinking about the algorithm we discussed in the beginning. But any lower bound argument has to work against all possible algorithms, not just the ones we described. Right? So we really do not know whether there is a better algorithm which doesn't send the characteristic vector but some compression of the characteristic vector. Right? So for example, under many scenarios, if you know something more about the set A, characteristic vector may not be the best thing to do. Like for example, if you know that Alice's set has only 10 elements, then the 10 log n thing, what he suggested might be the better algorithm. So we are here arguing against every possible algorithm. Okay. By the way, this game is not symmetric. If the communication channel was reversed, if Bob was communicating to Alice and if Alice wanted to figure out if Bob's favorite number is in her list, how many bits do you need? Yeah, in fact log n is enough. You just have to binary encode I and send, right? And since Alice has the entire set information, okay, so it's this n is nothing magical about n, okay? It can change depending on the game. Any further questions? Okay, so game 2. Okay, this is called the disjointness game. Okay, the locations of Alice and Bob hasn't changed. They are on opposite sides of the globe. The cost of sending bits through the channel hasn't changed. Everything remains same. What is different is this part. Okay. Now Bob has also grown up. Okay, he is not so picky. He is not that he just has one number that he likes. Okay, Bob also has a set B. So Bob knows you, both of them know. Okay, the universe is known to Alice and Bob. Bob now knows B, Alice knows A, and Bob is, his expectations have also come down. He is happy as long as there is at least one common favorite thing between, B and A. So mathematically, you are checking whether A intersection B is empty, in which case Bob will be dejected, or if A intersection B is non-empty, in which case Bob will be happy. Okay, so this could have been equally called the overlap problem. Okay, I mean, people chose to name it the disjointness problem because they are checking whether a set is disjoint or not. Equivalent to checking whether it is overlapping or not, just reverse the answer. Rest of the setting remains the same. The communication is only from Alice to Bob, it costs 1 rupee per bit. Okay, so here what do you think? Okay, first of all let's do the the algorithm part. What can we do? What can Alice communicate to Bob? Sorry? Yeah, in fact the same protocol that we did last time also will work, right? Alice can send the characteristic vector of A so that it is n bits, okay, to Bob, and hence Bob can then make the decision, right? Everybody with me? This time Bob has to do a bit more complicated process. It has to be like a search over all the entries in B. But we are not really bothered about the running time that Bob spends, okay? We just have to be sure that Bob will be able to do it. Okay. So here again, what is going to be the upper bound part we have already proved, okay? That f of n, the minimum number of bits is at most n. What is the proof? This is a proof by algorithm, okay, or a proof by construction. We have given an algorithm by which we can do it in n bits. The interesting question for this lecture is the opposite. Here, can we argue that this is the best possible? Can you show that in this game also you need to send at least n bits? Recall that our argument for the previous game, the key argument for the previous game was whatever compression scheme encoding Alice chooses, finally Bob should be able to distinguish the entire contents of A, should be able to distinguish the all of A. That was the key argument, rest of it was standard combinatorics. Does that observation apply here also? In this case, should Bob know entire A? Worst case, yes. Why do you feel so?
Because if he checks only one element and it happens so that none of the elements till the last element is in this set, then he'll have to check all the elements that Alice has got. So that it.
But for example, okay, giving a particular counter example to that is difficult. Like for example, if Bob had the universe with him, right? Then Alice needs to send only, one element from her list. She just have to say whether she has an empty set or not. Okay, as long as her set is not empty, Bob is going to be happy. So arguing for a particular example of a set B may not be the correct thing to do. So, but you are on the correct track. Just if you polish your argument, you will have it. You had another suggestion? No.
No, I was saying in the first game,
Ah.
we had only one element to check.
X. Yeah. Exactly. Yeah.
Yeah. Now we have a set of elements
Hmm.
to check. The rest of the set is the same.
Hmm.
So if the number of bits that Bob needs to have is still
Hmm.
to compare.
But you are correct in the end. But why should Bob know A entirely?
To match all the elements of B.
He needn't, right? As long as he even knows one of the elements in B is in A, he can be happy and forget about the rest.
It might happen that none of the elements that he has got is in Alice.
Yeah, you are correct. You are correct. You are correct. Okay, it's, as I told you, there is nothing great about the idea here. It's more about arguing it in a more rigorous sense. Okay, so let me say this way again. What was the key reason why the entire information about A had to reach Bob? That is because Alice did not know what index I Bob had. That applies now too. Alice doesn't know what is the set B. So B could as well have been singletons. Then it reduces to the previous problem, right? So if B had a singleton set which only had some single element I, right? And we do not know which I. So Alice has to make sure that whatever is the set that is with Bob, Bob will have to figure out an intersection. So in the worst case, Bob's set could be all possible singletons, right? In fact, this idea, this problem you can argue it directly also, but it also is good to know that this is the general framework of a reduction argument. You know that the first problem you needed required n bits. The second problem somehow looks like a special, the second problem that you are looking at seems to have the first problem embedded inside it as a special case when the set B is singleton. So you cannot do better than the simpler problem. Okay. In fact, this is indeed a much harder problem than the previous one. Okay. So for the first problem, under some other variants, you can, when you have multiple communication rounds, for example, if you have a 2-round communication, then suddenly the other problem becomes easy. Because if Bob can communicate to Alice, you only need log n bits, right? Alice's first communication would be empty. Bob, when it sends back, will send log n, then Alice has to just say yes or no. But this problem is even harder. Even if you allow multiple rounds, finally the total cost of communication added over all the rounds will again be n. Okay. So this is the second problem that we have to remember. And here again, please make sure that you understand the bullet points in this summary. If any point is not clear, please feel free to ask. Everything clear? No.
For any two different sets.
Yeah, correct. So in fact, when I first wrote the proof, the alternate proof in the yellow color is probably what I explained. But let us say you want to directly attack this problem. Maybe if I had posed this as the first problem, one way to think of it is, we have to argue that Bob has to know entire A, okay, which means no two different subsets A and A prime that Alice has. If Bob cannot distinguish it, I can always, because since A and A prime are different, you imagine them as Venn diagrams, there would be at least one element which is in one of them but not the other. Okay, it could either be in A but not in A prime, or it could be in A prime but not in A. If one is a subset of the other, we will not get it both ways. But there is at least one element which will be in only one of the set, not both. And Bob's set could just be the singleton which contains that one element, in which case if A and A prime are encoded to the same string by Alice, Bob will not be able to get the correct answer. Okay, that's the way I had posed it. But now when I explained, I kind of had the hangover of the previous problem. So it's the explanation I gave earlier was more as the more in tune with what I have written as the alternate proof. Okay. Okay. So game time over. Now we have to connect this to streaming algorithms. Okay. So recall, what is the basic setting of a streaming algorithm? Either you can think of as a stream of data passing through you and you are doing the computation. Equivalently, you can also think, the stream is static there and you are kind of walking over the stream, starting with the first element. You are like, then you step to the next, then you step to the next, and so on. And while doing that, you have very limited storage. You have just this one A4 sheet on your writing pad. You are only allowed to use that much space. But but you're super intelligent. You can do whatever computation you want. But in terms of storage, you are severely limited. That is the setting of the streaming algorithm. And when do you have to give the answer? Only after you reach the end of the stream. Okay. So here there are m objects in the stream. It could be numbers, bits, okay, whatever, okay, or edges of a graph like in the connectivity model. You walk over the stream one object at a time, do whatever calculations that you want to do, but the storage is limited to some predefined thing. Okay. So you have to remember these two key things. There is only one pass allowed. I'm not going to talk about multi-round streaming algorithms or multi-pass streaming algorithms here. One pass allowed. There is severe limitation in terms of space storage. Okay. So you would have seen these examples, right? You have an m-length stream, and this is the majority problem, the first one. You are going to check if there is one element which appears more than half the length of the stream. That's the majority problem. This is what Venkatesh would have told you. You have an n-vertex graph. Check if it is connected or not when you have a stream of edges. You can either think of you standing there and the edge kind of passing by you, or you take the active role, let the edges be all lined up. You kind of take your storage and walk along the edges. This you taking the storage and walking along the edges way of imagining it is how I am going to present it. Okay, but it's just a choice. Everybody, how the Ooty trip hasn't made you forget all this, right? This is the idea of the streaming. Now the key question: how do we connect these two? Is there any way for Alice and, am I in the correct page? Yeah. Can streaming algorithms come to help Alice and Bob? Okay. Remember, this is a tough slide. Okay. But this is the second most important slide. This is going to be the second most important slide in this lecture. When the first one comes, I'll tell you. It's like tough because I haven't even given you which streaming algorithm, and I'm not even saying which of the two problems that we saw. But forget all the details. Try to see what would be a possible connection between streaming algorithms and those games, that setting of those games that we are talking about. Okay?
That is for sending one bit of characteristic to the phone. But if she sends one by one bit, but there is one measure, how Bob will confirm that?
Good. So that's not the connection. Any other guess? This is guessing time. Okay. Actually, I will be completely surprised if you can find the answer. But I want to get you thinking. Because in fact, Arijit was telling me, in fact, that is why I kind of made this slide this way. That this is one of the key bottlenecks. The lower bound arguments all use this communication games, which on the face of it doesn't seem to have any connection to streaming algorithms. Okay. So we are kind of marrying two paradigms. One paradigm of streaming algorithms with another paradigm of communication games. Okay. So this is the the philosophical slide here. Okay. Any guesses? Okay. Let me. Okay. This is the connection. Okay. Let me try to describe what the connection is. Okay. So now this stream has two parts. The first half of the stream is in Alice's control. Okay, that is the A1 to AK part, what I have marked in blue. So Alice is in somehow her data that she has, it may be the set A that she has. In some way, she kind of encodes it and puts it onto the first half of the string. Okay. The second half of the same stream, AK plus 1 all the way up to AM, the ones I have highlighted in green, are Bob's construction. Okay. So Alice doesn't know what is the green part of the stream, Bob almost doesn't know what is the blue part of the stream. Okay. So this is the first idea. The people have their own responsibility. Alice is responsible for first half of the stream, Bob is responsible for the second half of the stream. Okay. And this streaming algorithm is an algorithm that is public. Now, Alice knows it, Bob knows it. So Alice gets a person or a computer to start this streaming algorithm from A1. Okay. And imagine the person taking this limited storage in hand, walking over the data, but he won't do the entire job. He will stop at AK. Okay. So this streaming algorithm is somehow interrupted at the halfway mark. Okay. You ask him to stop. Then what do? You take out his whatever is there in his storage. That's what I have tried to depict with this. You take over this writing board, whatever is in the storage of that. What is beautiful about what is there in the storage? Somebody else, somewhere else in the world can actually continue the algorithm provided they know what is there in this storage. In fact, that's the beauty of streaming algorithm, right? The only communication that this algorithm is holding to is what is in its storage. The algorithm is public, right? So what Alice does is you run the streaming algorithm for her part of the stream. At the end, you steal the notebook from the algorithm and communicate it at this rate of 1 rupee per bit across the world to Bob. Now Bob also knows the algorithm. He commissions another computer or another person to finish the rest of the task, but Bob starts with the storage that Alice had communicated. So it's as if whatever the streaming algorithm has stored so far, which is all that is relevant when it comes to the final answer, Bob's agent already has it when he starts it. And when Bob's agent will run through the rest of the stream, do whatever this computation that was required by the algorithm, and finally when he has finished the stream, he will look at the storage and do whatever time consuming task is to be done and return the answer. Okay. Is the overall setting clear? I have intentionally left it vague. I am not speaking about the particular problem here. I am saying this is the basic idea behind connecting a streaming algorithm and a communication protocol. What is being communicated is the storage in the streaming algorithm at some smart point in time. Okay. So the stream is broken into two. There is Alice's part of the stream, which is run by this algorithm, and whatever is the storage, the memory content of the algorithm at that time is what is transmitted over the globe to Bob, and then Bob has the same algorithm running here, but it is kickstarted at an intermediate point using the memory footprint of the algorithm. Okay. Ask me if it's not clear. Shall we then apply this setting to a concrete reduction? To a concrete, yeah, you have.
I'm wondering how it is related what we discussed in the first name. We are just discussing about the streaming algorithm. What we want to do, like it is sending some messages. Bob wants to verify.
Exactly. So that's my next slide. Okay, that's my next slide. So I'm trying to make this concrete with one question. Okay. So here we have two things. On the left side, this is the index game, the first game that we saw, and on the right side, this is the majority detection in a string. Okay. So here I just again in the majority detection, let me recall, you have a stream of numbers A1 to AM. You want to check if any number appears more than half m times. Okay. In fact, to keep it simple, I don't even bother which number. I just have to detect if there is one number which appears more than half the times in the stream. Okay. So if the stream is like 1 million, 2 million long, I'm checking even if there is one number which appears 1,000,001 or more times. Okay. So strictly more than half the whole length of the string. Is the second problem clear? Is the majority detection problem clear? Okay. Now, exactly the question you asked. Now Alice's and Bob's task is clear. It is the first problem that we discussed. Bob has a I element of U, a single number with him. He wants to know if I is a member of Alice's favorite set A. Assume you are all, because you had 1 week of this program already, you know how to do majority detection, right? Using very small amount of space. Can you find a way to help Alice and Bob? You want hints? I'll put the basic setup, okay? Try to fill in the details. Okay, so this is the basic setup I told earlier. We will be splitting the stream into two. The first half will be Alice's responsibility. The second half will be Bob's responsibility. Am I doing something wrong? Done? Okay, thanks. I hope I'm still audible, right? Okay, so yeah, so tell me, and we already know what is the algorithm. We are just going to run majority detection, algorithm, right? That's the only, let's pretend that that's the only streaming algorithm we know. Can we use this majority detection streaming algorithm to help Alice and Bob solve the membership game? Okay, so this is the concrete question you asked about.
Will be A. If I belongs to A, A is a stream of elements. So I will appear 2 times.
Very good. Okay, so I'll try to put, what's her name? Ami.
AMI.
So what Ami is suggesting, at least what I think she is suggesting, is that the first part of the stream somehow will have numbers from A. Okay, since A is a set, in a set a number appears only once, all the numbers in A will appear roughly, exactly once, right? And Bob in his part of the stream will put just that number I, with that he wants to know whether is there in A. Okay, so if I is in A, in the whole stream I will appear twice, once on Alice's side and once because Bob put I into the stream. If I is not in A, then I will only appear once. Is that clear? Is that clear? So if you had something like a repeat detection algorithm instead of a majority detection algorithm, this would have worked. Okay, what is a repeat detection algorithm? It's a streaming algorithm which would check if in the stream any number is repeated. If you had a repeat detection algorithm, Ami's algorithm would work. But we do not have that. We have a majority detection algorithm. So there is just one smart step more. The starting is correct. There is just one smart step more to use majority detection. Okay.
So binary 1 0 1 0. You can count number between index.
Yeah. Now actually you are going away from the answer. You are getting, the earlier attempt was very close to the answer I have in mind. Get creative, it's your chance to help Alice and Bob. Okay, one more hint. Try to play with the Bob's part of the stream so that if I is in A, I doesn't just become a repeated entry, it becomes a majority entry. Okay.
Bob knows how many elements are there in A.
Very good question. So actually it doesn't, but as the first part, let us assume Bob knows.
Then Bob can send A times I.
Bingo, perfect. Okay, I'm very happy that somebody answered it. So suppose Bob knew the cardinality of A. Let us say A was 100. Cardinality of A was 100. Then what Bob will do is not just put one copy of I in the stream, it will put 100 copies of I in the stream. So the total length of the stream now becomes 200, which means the majority detection point is